Okay, now we will go into the Hamiltonian mechanics. So the characteristic of Euler-Lagrange equation in classical systems is that it has the acceleration and second derivative. And then characteristic of Hamiltonian mechanics is that it only has the first derivatives. And then it has things like symplectic structure and relatively good theorems, so there's like strong mathematical background. So we start by looking at the L, which depends on Q and time derivative of Q. And then we look into doing transformation to this. It's called the Legrand transformation. So, and how you define the Legrand transformation is that you find the supremum of the Legrand transformed quantity times the function times the variable minus f of the variable. So this we will do the Legrand transformation with respect to the time derivative in order to get rid of that. So we will call, so we say sup, and in the domain of x, so meaning in the domain of so we will find minimum or supremum value of the time derivative in such way that we have the time derivative times and something new. I will call this p, and then minus L of this one. So now the qt, so the first coordinate L depends on it. Now it's taken to be constant, and I will call, so the h will again depend on the q, but now it will depend on p. So there's so let's see, I will remove the t dependence here because these are not yet okay. So I think this is the dot q. Why don't you show? Okay, let's put some. Okay, and so how do you solve this? You solve for the stationary point with respect to dot q. So it means that we can need to take derivative of this expression. So essentially we get that we take derivative with respect to q dot of that thing here. So whoa, what did I do? Okay, whoa, what is going on? So I take derivative of this thing with respect to dot q, just so that I can and that will be given, so that it will be p, so and then minus, and then derivative of the L with respect to dot q, and that needs to be taken to 0. And here we have then we basically have a definition of the generalized momentum. So this p, the new coordinate we introduced, which was introduced by doing Legrand transformation to the time derivative of q dot, we get very simple. So it's the partial derivative of the Lagrangian with respect to the time derivative of the coordinate. So let's write that up. So to find supremum with respect to dot q, we need to take the derivative of the expression and then this, which defines the generalized momentum directly. So we have that the P equals to this one. So then there's something, so this no longer depends in, so the left hand side does not depend on Q dot, so meaning that the right hand side does not depend either, and that's because it's minimized over. So essentially we have re-derived the equations again. So so we can now, for example, we have the Lagrangian of the harmonic oscillator. So that one, and so first we can calculate P with respect to that. So we take partial derivative of Q, so we get M, P is M equal dot Q. So this is the typical definition of momentum. So there was nothing so weird about that. And then we just, if we follow this, substitute back, so we have solved for P, so we can then so the dot Q can be then written in terms of P as 1 over M times P. So we have that the value of this thing when under minimization condition, so we have HQP. So now we have P, selected P in such way that it actually minimizes. So we have here dot Q, so we have 1 over M times P squared. So now suddenly we actually have written this as momentum, and then minus L, and in the L we also need to write the dot Q in this way, so I will do that explicitly. So the L in case of the harmonic oscillator looked like this, and again in the, so we have 1/2 M and then dot Q, but the dot Q was actually P divided by M. So we have 1 over M squared and then 1M here. So we will end up having 1/2. So we will end up subtracting 1/2 over 2M P squared. And then we have here minus 1/2 omega Q squared. And then there's one more minus in this minus L, so it will end up as plus. So we end up having something like this. So something like this, and then the, so we can then combine these two terms. So there's like 2 times the kinetic energy minus the kinetic energy, so it will end up as the kinetic energy and then as the potential energy. So this is just the typical T plus V, so definition of the Hamiltonian. And then we will so I wonder, can I derive by heart the Hamiltonian equations from this? So basically the dynamics given by Euler-Lagrange equation should, like, one can derive the Hamiltonian equation of motion from this, so I can just write them. So the Hamiltonian equations of motion are now given as, so we have dot q equals derivative of Hamiltonian with respect to p, and then we have dot p q, like so. So I will pause for one moment and figure it out. How can I derive it? Okay, I think I can figure out how to derive one of the Hamiltonian equations of motion. So we have here, I copied the Euler-Lagrange equation, and here we see partial derivative of q dot of L with respect to q dot, and we just noticed that this actually was p. So we have time derivative minus time derivative of p, and then we have time derivative of L with respect to q. So we can so the point is that Hamiltonian no longer depends on q dot. So I think I can then just like substitute L with h here. So we are not, because we are not changing the coordinate q at all. So the properties of the function with respect to q should stay the same. So I think like that we can derive the first Euler-Lagrange equation, just that it will, so this one will become dot p. So we can call, yeah, and then this will be minus frac partial L partial q. So that's sort of so I think I can just do this. I'm not actually sure, but this is now the first Euler-Lagrange equation, and for the second one, so q dot, so we have so no, wait. So okay, let's start over. This we know that p is as such. We know that, like so. So then we can take time derivative of that one. So we get dot p, and then we get this one. So now we have done at least nothing wrong here. And now we can look at the Euler-Lagrange equation. and we see that it actually contains this part. So we know that the dynamics fulfills the Euler-Lagrange equation. So we actually get that minus this one will be this one. So dot P will be frac partial L with respect to partial Qt and with a minus sign. Okay. So and then we have to have dot Q, equation for dot Q. So how do we get that? So we can okay, I decided that I'm not gonna do that. So here's the derivation of Hamiltonian's equation. So you can see that it's relatively lengthy and based on variational calculus and some insight of what to do, and then you sort of have variations of the Lagrangian and Hamiltonian, and then you can identify some terms, and then you will eventually lead into the Hamiltonian's equation of motion. And you can see that this is yeah, there was no way I was going to derive this by intuition, so no wonder why I failed. But that was not the main point really. The main point is that this depend on the first derivatives now, and then we can introduce the Poisson brackets. So and this will give us a nice view, a nice sort of notation for the system. So the Poisson brackets are defined as, so we have some function of Q and P, and then we have some another function of Q and P, and then we can define the Poisson brackets in such way that well, there might be many of these variables Q and I. So we can say that it's like a vector. So I will make a bold. Like so. And then the Poisson bracket with respect to that is given so that we take derivative of f with respect to q and multiply it with derivative of g with respect to p of that coordinate, and then minus, and then the p and q switched like so. And we can just okay, let's just check that it's correct. Yep, we can change the d's to partial. So this is the definition of the Poisson bracket. And the thing is that we can now write the Hamiltonian equations of motion in a very simple form. So suppose that the function g just depends on qi. So suppose g of q and p is just q. And then the Hamiltonian equation of motion for q written as. And then will also be defined an f qp equals Hamiltonian of q and p. So so we can see that since g only depends on q, only here this term will become 1. So means that we have minus and then partial derivative of the f, which is Hamiltonian with respect to p. So we have actually that dot q equals to the Poisson bracket of Hamiltonian with respect to q. And we can actually have the same for the p. So both of these will actually equal to the Poisson bracket as such. And this is for time-independent Hamiltonians. So we may write a general vector. So we can use like write jet, just combines all the generalized positions and generalized momentum. And so we have the equations of motion. So we can just write them as such. And now we are going to go into the split propagators. And so we can formally solve so that so let's so we say that we have some jet, and then so we can write the time derivative of jet in this way. Then, and this one we may then obtain by just solving for the value at next time step. We will get it that it's the value at this time step plus the Poisson bracket and times dt. So essentially we may then add these together. So let's suppose we have something like this and we multiply it again and again and again at z equals 0, and then we get eventually the thing at z equals t. And for example, for time independent Hamiltonian we actually can, so we have I'm having t, so let's just rewrite this again. So it's like 1 plus this one dt times the z at t. So now it's sort of so this was too much here. So now we have suppose we have n steps and total time of t. So one step is t divided by n, and then we take this to the nth power, meaning that we operate n times with it. So we have something like chat t equals to this one. And now now we take the limit of n to the infinity. And this is exactly the definition of the exponential. So we can write this as exponential, where the exponential, it is with respect to the Poisson bracket. And one more thing. So okay, now it starts to look good. Yeah, so this is the kind of operator here which propagates it a little bit forward in time. So this means that the central dot here means that it will operate on the function z. And then, so now the problem, of course, is that how to make things numerically stable. So let's go to the symplectic split propagator. So I will show you what I did. So firstly, let's show that we can calculate this. So this is extremely complicated thing. So we have this abstract operator exponentiated. So one more thing. There needs to be a time ordering operator. So Hamiltonian on different times. Well, I just said it's time independent. If it would be not time independent, we would have to have the time ordering operator here, so that this t is at different times. But now it's okay, and we can keep it that way. So let's suppose that the Hamiltonian only depends on generalized momentum. So we have HP. And then we want to calculate this thing here. So we want to calculate the Q and the P of this thing. And so we can write this expansion using the Taylor expansion. So we have Okay. And now, since the Hamiltonian, so first we can look at this term where the Hamiltonian depends only on p. So in the Poisson bracket definition, you will only get this side. So you only will get partial derivatives of this side. So we will actually have that the other function will be partial derivative with respect to q. So it means that it only will affect the term in this side q here. And essentially, if you do it twice, this will be 0. So we actually have that the HP and then HP and anything will be 0. We actually have that this one is exactly given by this expression here. So we can exactly solve it. So now we can and what is important is that this is so-called canonical transformation as well. So you can we're doing infinitesimal canonical transformations, which are time translations. We are moving the system forward in time. And now I showed you that we can do this exactly. So this is an exact canonical transformation. It means that it will preserve the symplectic structure of the system. And therefore, it means that it can it will yield into symplectic propagators, which conserve the volume of the phase space, which makes the propagator very stable. So if we split h into t plus v, we can calculate exactly. Where this one depends only on p and this one depends only on q. We can calculate the exactly as given by t, b, and q. And then there will be errors related to the non-commutativity of t and v, but all the transformations forward in time are anyway canonical transformations, thus preserving the symplectic structure. Okay, so what I mean exactly is, thus a good propagator is given as so we do e power to the t c dot dt, then divided by half. So I'm using the half because it increases the accuracy even more. So we are like approximating this one with this one. So let's see how it went. Okay, so this is what we did in the MATLAB example.